Okay, so next is where the fun begins with our task number 2, MPLS 6PE. Now we need to configure BGP session between R1 and R2 to advertise IPv6 routes. So we need to source our session using the R1, R2 loopback 0, and then we need to make sure that MPLS labels are exchanged within those sessions. And when we are done with the configuration, we need to verify connectivity between all of our IPv6 devices. Okay, so now we are at the point where we're going to be configuring this IBGP session right here, and we want to make sure that we are advertising all the connected subnet as well as the taking care of the redistribution, since we're not running BGP end-to-end. So, or for the site that's running Ospf, we have to redistribute Ospf into BGP and vice versa. And for the site that's using static route, we have to do static route redistribution of the static as well. Okay, and this is true for both R1 and R2 since both has the Ospf protocol running as well as the site that use static routes. Another difference, you compare this to the multi-protocol BGP, or specifically VPN v4. BGP with the MPLS VPN is that by default we configured MPLS VPN. The label for the VPN v4 routes are exchanged automatically, but for us here we're going to have to use a send label command as part of the BGP configuration to tell our PE routers to specifically send the labels for those IPv6 routes. Okay, so we're going to start our configuration off on the router R1. So first we enable our BGP, and our AS number is AS100. So router BGP 100. We'll do a basic configuration with no auto summary and no synchronization. Okay, and then we give it a router ID using its loopback 0. So it will be 172.16.0.1. And since we're not dealing with IPv4 BGP here, we can just, although not required by our task, disable IPv4 unicast. Okay, next we define our neighbor 172.16.0.2 RT loopback 0 with the remote AS of 100 since we're doing IBGP here, and then we are sourcing of the BGP traffic using loopback 0. Okay, next we get into the address family. Because when we have the session configured, next we get into the address family. You can see right here we have IPv6, and here we have 3 options just like the IPv4. We are only dealing with unicast at this point, so we specify unicast. Next video we're going to look at the VRF, which is the 6PE. For here it's just unicast. First we'll use a network command to advertise the directly connected network, and this is for the link between R1 to R6 and R1 to R8. And the first network is 2001.66.16 /64, and then we have a 18 as well. Next we have to activate our neighbor. So activate as part of the address family. So we have too many 16 in there, right there. And then the crucial command that you need is send label. Okay, this is to let the router know that it needs to attach a label along with the routes. And now we have to take care of the redistribution. So first we redistribute from Ospf ID 1. If you want to include connected subnet, you can do it right here too, but since we already used the network command for that, there's no need for us to do that. And then we also need to redistribute static. Okay, though always use route map with your redistribution, but here we're just going to keep things simple since it's only a lab, so we're not going to use any route map here. Right, and that's just redistribution in one direction. We have to take care of the opposite direction under the Ospf. We have to redistribute from BGP 100, and when you redistribute between the 2 routing protocols, it's always a good idea to tie or give it a metric value for that. So here, let's give it number 3 so we can easily identify that. And then don't forget to redistribute static as well for R6 to reach R8. And now if we do a show IP, okay, so it's still a show IP BGP, not so much of a show IPv6 BGP. So show IP BGP, and here we have an option to specify that we want to deal with IPv6, and it's going to be route of type unicast. Okay, you can see that all of the routes from right here, R6 loopback, has been installed into the BGP table as well as the static routes that we have for our R8, and obviously the directly connected route that we use a network command to advertise. Okay, so we're pretty much going to repeat the same process for R2. So what I'm going to do, I can just copy what we have configured so far already and put it on Notepad. We copy that, make sure we do no auto and no sync. Router ID is 2. We keep that, that's the default, so we don't need it. Neighbor, it's become a router 1 since we're going to put this on router 2. 1, 1, and then local subnet for that is, I believe it's 27 between R2 and R7, and 102 between R2 and switch 1. Okay, we still need the redistribute Ospf and redistribute static. Okay, so let me copy all that and paste it on router 2. Okay, so while that's coming up, let's take care of redistribution into Ospf as well. So redistribute BGP 100 metric 3 again, and then redistribute static. Okay, then we double check. Now BGP table would show IPBGP, IPv4 unicast, and so far it already has the routes to R7 loopback interfaces as well as the static routes to switch 1. Just going to have to give it a few more seconds here for the BGP session to come. It looks like BGP session actually came up already. It's just the route that hasn't really been exchanged yet. So let's give it a few more seconds. Alright, looks like the routes came across. Now let's go back to router R1 and make sure we're seeing the same thing on the R1 side with the summary. Okay, as you can see, it's 6 routes as well. And here R1 is seeing routes to R7 loopbacks, R8 static routes, and the 2 locally connected subnet of R2. Alright, so let's try to dig a little deeper into these routes. So if you do a show IPBGP IPv6 unicast, and you can see the question mark, all the commands after that will look just like your regular show command for BGP. You just need to make sure that you start off your command in this format for IPv6. And then let's say we want to look into detail of a route to R7 loopback 10. You see that's being learned from a router R2, although it's kind of an unusual next hop format with the quad F that precedes the IPv4 format of the router, of the source routers. And then this is just a regular BGP attributes, and right here at the end, since we asked the router to send labels, R2 is sending a label of 27 along with that particular routes. Okay, so make a quick note that that's a MPLS label 27 for R7 loopback 10. Same thing if you do show MPLS forwarding for same routes, you see that the outgoing label for that is also 27. Okay, the next hop is the physical next hop. You can see right here we have a router 3, which is our P routers. Then if you do show IPv6 Ceph of that route, you will see that the router is getting ready to prepend 2 MPLS labels to the packet that goes towards that subnet. So 27, we already know that's the bottom label. 18 right here is the top label, and that's the label that's going to help getting the packet from R1, which is the ingress router, to R2. Again, same concept as MPLS VPN, and we can prove that. Do a show MPLS forwarding label looking for 18. Okay, so 18 is getting you to the router R2. Okay, that's R2 loopback 0. And now if you do a quick trace routes, okay, to do a trace routes, you might need to do an advanced trace. Just trace enter, and then instead of IP, we're going to be doing IPv6 trace routes, and the target for that is 2001.7.1, which is our 7 loopback 10, sourcing from, let's say, R1 interface right here. So that would be 2001.00.16:1. Just enter all the way through, and you can see that the first hop packet has the label of 18 and 27. Somehow we're missing the bunch of hops in the between. Let's try it one more time just to make sure. So that would be IPv6, that, and that. Looks like we're getting pretty much the same thing here. It could be that we have a load balancing going on from R3 to R4 and R5. So let's take a quick look. Okay, looks like it's pointing out both ways. So let's maybe disable one of those paths. So let's disable the one that goes to R4. So shut that down. Do another trace routes. Okay, looks like at least we got the final labels before it hits R2. So you can see that leaving R1, it has the, I believe it was 18 and 27. So by the time it gets to R2, with the PHP, the topmost label got stripped off, and then it's just left behind the bottom label, which is 27. Again, same behavior as MPLS VPN, and that is for the IPv6 label that's got left behind. Alright, so hopefully at this point we have the full connectivity between the sites. So let's go ahead and verify that, starting at router R6. Do show IPv6 routes Ospf. Oh, actually it's right there. So R6 has received the subnet VLAN 27, VLAN 102, and then all this R7 loopback addresses, and then the static routes to R8 as well as static routes to switch 1. So right now if you're trying to ping 2001.7.1 sourcing from loopback 10, you can see that pingable, although it looks like we still have the packet loss between R3 and R5 still. It's something that I noticed earlier. We're trying to set up the lab, so let's do this. Instead of path to R5, let's force it to go through R4. This shuts that link down. So now we're going to force traffic to go from R3 to R4 instead of R5 and see if that helps with our packet loss right there. Give it a second. Okay, so you can see that we can pretty much ping without packet loss right now. And if you're trying to ping from R6 to, say, R8, it's pingable, that's local, and then to switch 1. And that is pingable as well. Okay, so let's try that also from, let's say, switch 1. Ping 2001.6.1 sourcing loopback 10. Okay, pingable to R7, that's local. That's pingable, and then to R8. Okay, we can also try and also loopback 11 as well. That should be 0.1. Okay, and then 0.2. And looks like we have complete connectivity between our 4 IPv6 sites, and that should complete our task number 2. Again, all these are working based on the concept of tunneling, but instead of using the extra IPv4 header for the tunnel, we are using MPLS label instead. And like I mentioned at the beginning of the video, all of these are very similar to MPLS VPN, where you see 2 MPLS labels in the label stacks, with the topmost label getting the packet from the ingress router to the egress routers, and the bottom label is for the final destination. And throughout the configuration in this lab, we didn't even need to touch the P routers. That continues to run IPv4. It has no idea the traffic that it's carrying is actually IPv6. And obviously all of these can operate in parallel as your regular IPv4 routing. So if you are running IPv4 MPLS today and would like to start implementing IPv6 but do not want to start replacing your core with IPv6, although I'm not really sure if IPv6 MPLS is even supported at this point in time, in that case then you can just pretty much leverage your existing IPv4 MPLS to transport all of your IPv6 traffic and start interconnecting those IPv6 sites. Alright, and that should pretty much wraps up our video on MPLS 6PE. The next video we're going to look at the variant of this with the addition of VRF. So we're going to implement actually the MPLS VPN with the sites being IPv6 sites. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching LabMinutes.com, and I'll see you guys in the next video.